whenever we think of humans going out and colonizing space, like leaving Earth and actually building homes somewhere else, we generally think of planets, which is a mistake. It's a total, absolute mistake, as the numbers are just compelling.
Lies the future of humanity, a second home far beyond the Earth. This might be our most exciting vision yet for a colony on the planet Mars.
The next step in space exploration isn't generations away. It's happening right now. And our destination? That mysterious and desolate world next door, Mars. What would happen if we built a city on Mars?
Which is a mistake. It's a total, absolute mistake, as the numbers are just compelling. The numbers simply say that we are not going to live on planets, we are going to build space habitations. Take Mars, for example. Mars is the obvious candidate for colonization because, well, firstly, it's in our solar system. Secondly, for a very long time, people looked at it through their telescopes and they saw what they thought were canals, and then people wrote books about Martians, and so it seems like the obvious place for us to build our next home, but it is totally wrong. And you realize that it's totally wrong once you have the design for a space habitation. The point is sustainable carrying capacity. How much carrying capacity does Mars provide compared to how much carrying capacity will space habitations built using the mass of Mars? How much will that carrying capacity be? Now, Mars is quite yummy. So, you can it can be disaggregated and used to build space habitations. It's the escape velocity from Mars is only 5 kilometers per hour compared to about 11 kilometers per kilometers per second compared to 11 kilometers per second for Earth. So doesn't require a whole lot of kinetic energy to get from the surface of Mars to space. Okay, the mass of Mars, now we are coming to the real point. The mass of Mars is about 6 into 10 to the power 23 kgs. If you were to break this up, you could have 452 billion space habitations. And why is it that you're seeing this number here? What is the background to this number? The background to this number is the calculations for the amount of mass it would need to build a space habitation, which was actually discussed in the earlier videos, and that was 1.42 trillion kilograms. So Mars, if you were to break it up and you send it to space, you could be able to build 452 billion space habitations, and each space habitation would have 50,000 humans living in them, which is about 22,000 trillion humans. Compare that with if you were to actually colonize Mars, how far would you get? Well, I mean, very optimistically, like something like Earth. Mars is a lot smaller, so it really won't be like Earth. But suppose you even got to Earth, and how much is that? That's 10 billion. So you on one hand have 10 billion carrying capacity if you colonize Mars. On the other hand, you have 22,600 trillion. So that's like 2.6 million times more than 10 billion. So you can actually provide home for 2.6 million times more humans if you were to break up Mars and build space habitations. And can you actually break up Mars and build space habitations? Well, then there are some issues about, okay, it comes down to energy, and it comes down to how much energy does Mars receive. And there are some calculations for the energy per unit time in terawatts, how much it does. So the power available from solar panels, if you cover about 50% of Mars, will be 6,495 terawatts. The amount of energy needed to spend 1 kilogram from the surface of Mars to outer space is 12.63 megajoules, which tells you that to send 1.42 trillion kilograms to outer space from Mars using this energy would require about 3,600 seconds. That's about an hour. So you can use the solar energy which is falling on Mars to send material to outer space to build space habitations at the rate of 1 space habitation every hour. Now, there are some other more precise calculations which are done in the book, so you'll have to get the book for that. And then similarly, we are going to eat Venus at some day. Okay, yeah, by the way, let me just say that, so all of Mars will take about 52 million years to eat, and then I think after Mars we'll move on to Venus, or maybe we'll do it in parallel. So there'll be challenges, but again, who knows what our technology will be? Well, I know, or I believe I know. Our technology will be 100 years, 1,000 years from now. And I think the way we'll proceed with Venus is we shall first siphon off the atmosphere, use the atmosphere to for whatever ways we can use it in our space habitations. And we will then, Venus's atmosphere is mainly carbon dioxide. And carbon dioxide and hydrogen together give you hydrocarbons, which can be used as many things. It can be used as building material, and also the atmosphere of Venus will be quite useful to for the purposes of space habitations. And remember, this is all automated. This all is going to be done by robots, so we won't really have to go and take it a little bit at a time. No, this will be done by massive machines with minimal human input, and that's where we shall be. You'll see that the atmosphere of Venus is being siphoned off, and then after the atmosphere has been sufficiently reduced, we'll actually be able to put mining machines on the surface of Venus and then eat Venus, just like we'll eat Mars. But we'll eat Mars first because Mars is much more easy to mine. It barely has any atmosphere. Its escape velocity is low. Okay. So there you have it. We are not going to colonize Mars, we are going to eat it. By far the greatest project of humanity. It's like we are living in this little speck in the universe, and then humanity is going to colonize space, and it's going to start from this little speck, and it'll expand. It'll first expand throughout our solar system. You know, hundreds of thousands of trillions of humans in the solar system. Next, our galaxy, and finally other galaxies. Okay. So, one thing you have to remember about this whole thing about space colonization is that normally humans conceive of projects which they can complete in their lifetimes. You don't really, like, people don't start, like, you can't think of any project where, any engineering project where they said, okay, this is going to take us 200 years to finish, or this is going to take us thousands of years to finish. Normally, you think that, okay, if I'm going to start a project, I want it done around 30, 40 years. Now, space colonization is not going to happen in 30, 40 years. It's going to take a lot longer. However, what we can do is we can break it up into smaller parts, and we can see progress. So let us look at where we are with this space colonization. Now, there are two aspects of space colonization. One is, social psychological, the very desire to colonize space, and that is discussed in the first part of the book. The next is the engineering issues, the science issues, and so here I am talking about the science issues, and I want to talk about in this video where are we? Are we making progress? Well, let's take a look. So here is the President of France giving an address to the United States Congress, and in that address he says, by polluting oceans, not mitigating CO2 emissions, we are destroying our biodiversity, we are killing our planet. Let's face it, there is no planet B. And next we have the Secretary General of the United Nations, and what does he have to say? Well, as I said often, we don't have a plan B because there is no planet B. Next, let's move on to the Scientific American. So here is a Scientific American article from 2014. And again, we have, let's remember, there is always a plan B, but there is no planet B. And one more Scientific American article. The world needs a plan B given its dire state. There is no planet B. So why are all these people saying that there is no planet B? Because they are essentially saying that we have a climate crisis and the Earth is our only possible habitation, and therefore, as there is no planet B, we are all stuck. We are stuck on Earth. We are not going anywhere. There's no possibility. There's no planet B. That's it. That's our future. We are here on Earth forever. No planet B. That's just bad science. It is bad science. As the calculations in the book, in my book shows, just our solar system, okay? I'm not even talking about going outside our solar system. Just our solar system, which is in relatively easy reach. There are mass and energy for 438,000 trillion humans, which would equal a population of about 54 million Earths. I consider everything in the solar system within easy reach. It takes about a year to get to Mars right now, whatever. I'm not even thinking about other galaxies or anything like that. So there's not just one planet B that we could go to. There are actually something like 54 million of them within easy reach. Present knowledge of the laws of physics, is it possible to actually build an interstellar colonizing vessel? Okay. So I'm going to describe the design of a vessel, and it's important to understand that these are all consistent with what we know of physics now. There is nothing like, oh, that someday we're going to do like wormholes and we're going to travel faster than light, blah, blah, blah. No, none of that. Okay. This is proper science. You don't say those things if you're a proper scientist. Love to be proven wrong, but I don't think it's going to happen. Okay, so what is the design for this colonizing vessel? Well, essentially it is based on the design for a space habitation with an engine added to it. Okay, and there are some design goals for it. The first goal is that the population of a ICV flotilla, so there'll actually be 10 of them. Okay, so there will be 10 of them in a flotilla. It won't be just one spaceship by itself. That's like kind of risky. You'll get bored. You want a variety of landscapes. One ICV will be like a tropical island inside of it. The other one will be like a alpine mountain ranges, and another one could be just a city, a major city. So just a variety. That's one thing. The second thing why you would rather have a flotilla of 10 ICVs rather than one ICV is that it reduces the risk. If there's some damage happens to one ICV, then the remaining ICVs can help repair it, or they can evacuate the inhabitants. So this design for the flotilla is based on 10 ICVs in the flotilla. And the total population of the flotilla will be 12,500.